So we don't use solar panels. We're also not using nuclear, but we could use a very cool differential pivot. So this was the previous version of the rover that was active for solid 5 years, designed at JPL. It went to Burning Man. We had lots of schools building this thing. Here's a little rover at Burning Man. I didn't do that. And these are, various people building the rover. We had dozens of people building one, and it became this community over time. People asked questions and helped each other and did really cool stuff. So it's one of the most starred open source hardware projects of all time, and by a large margin, even more than the open source hardware printers, 3D printers that are there, and it's been consistently active for the last 6 years. So continuously people making pull requests, making updates, making improvements, and we have a big growing community. Active Slack channel, that's a newer thing that we have, but it's really fun to see people from ages 8 to 80 building these rovers and helping each other out. So just to put that in perspective, here was 2 LinkedIn posts that people randomly, that I picked out recently where they're showing all the other open source projects. So I picked through them to see what the communities were like there, to give you an idea of how big this is. So a lot of these are sadly under-documented. The smaller robots are indoors only, or just kind of more of toys. They're extremely expensive, and you can see the number of stars that they have: 193, 400, 16, whatever. Even the famous turtle bot is doesn't have the strongest community. So I want to talk about why this really matters. Well, why do you care about stars, right? If you guys have looked at a GitHub repo and you see that there's 2 stars or 0, you're probably not going to assume that it's very well supported, robust, and you're going to find a community of people who are going to help you out with any questions that you have. So it's kind of an indication that is this circle where people see more stars, they come and join, they contribute, they build stuff, and then now you get more people to do it as well. The other reason that it matters is, you get more maintainers this way. People eventually join the team and start helping, and this is important because parts go out of stock all the time. So we need to make updates. There's newer, cheaper components that become available. The new Raspberry Pi gets updated, new motor controllers. People add fun modifications or additions, draws more people in, improved documentation, improved code, all of that kind of stuff, bug fixing, and then especially help from other builders. So if you're a 14-year-old and you're building this and this is your first robot, it's really awesome to be able to ask questions and get hundreds of people who are looking at it and building it. This was a cool one that I recently added. Some researcher was working on this, and they wrote something about ontological modeling language. I have no idea what that means. Half of the words on here I don't know, and it's for the open source rover, and it's really awesome to see because I don't understand half of this, and I will learn something new from these people working on it. So nice, teach me some words. So how do you go and build a community like this, right? How do you get to such a thriving community? So one thing that helps is to not start from scratch and build your own thing. Hop on the bandwagon with something that was there already, and there's many cool open source projects that you can join. It really helped that we had the NASA-JPL name behind this. But I think if you just release a project like that into the open and you don't keep maintaining it, it will eventually just die. You need people to be working on it. And so the first ingredient for that is excitement. You need to be on the road, giving talks, and getting people stoked about how cool the project is that you're building, how cool this robot is. Do demos and show what you could build with the rover after, right? This I'm manually operating it right now, but you can do autonomy, you can do some kind of cool new ML on it, to machine learning to do any kind of crazy tasks, reinforcement learning to climb stairs, all that kind of stuff. Always be launching some new feature and update. So YouTube's not working, which is kind of glad about, because this is a video of me skating behind the Mars rover, and I'm like wearing a helmet, and I look like the biggest nerd. That's right. That's right. Which is also funny because this was in San Francisco and everyone was so used to robotics already that no one like blinked an eye at it. A couple of years ago there was the AWS-JPL Open-Source Rover challenge where people did reinforcement learning in Gazebo, and it was cool because we got a new influx of people who were like not necessarily roboticists or hardware people who could then get used to the robot and then actually start building it themselves. Today's launch, we recently got open source hardware certified. Yeah. We made it to the front page of Hackaday, which has kind of like always been a personal goal of mine. And I recently built a little modification with a payload carrier on top. This robot can comfortably carry like 20 pounds, can pull more if you're putting a little basket on wheels behind it. So I also have a blog out there and videos out there if you want to see me have this robot follow me around and carry my groceries for me. Second ingredient is always improving, right? A lot of open source hardware projects out there in a repo, and that's cool, and it makes sense in some ways when you're trying to retain the old thing that you've built and kind of separate your concerns. But it also means that you lose some of that community when you make that transition. And so this was kind of like on the outset with the rover, is like we're going to make big changes to it. The first version of the rover looked drastically different than what we have now. And we're going to try to support the older versions, but the mantra is always keep improving, changing it. And so this rover is not going to look the same in a year from now. And that's a good thing. So the previous rover looked like that. If it rained, all those holes were not a good idea. So don't take it outside when it's dusty. I'm not going to say that this is completely weatherproof, but it's a lot better. You can take this out into the desert. You can take this out into some splatters of rain, and it'll be fine. I've tested that. So this is a slide from 2021. This rover costs 2.5K, 3K. You have to source parts from all over. So you spent half of the time on the project actually like getting the parts from various manufacturers. To take a step back, it was awesome. It was a great starting point. I don't want to completely tear it apart. But it required off-the-shelf parts. It required machining, 3D printing. It was kind of like everything, and it just meant that people sometimes would start the project but never quite finish it. And that is, of course, a huge problem, because what we want to do is get people to build this in relatively short time, learn a lot of the skills associated with robotics, embedded, all that kind of stuff, software, but then be able to do the cool stuff that they wanted to do on top of it anyways, right? The cool autonomy or racing or whatever people want to do. It was hard to get access the electronics on the inside. You have to unscrew it. The PCB was attached to the top, so people typically flip the rover over, which is, we've seen how hard it is to pick it up. Flipping it over is like crazy endeavor. So we set out to basically rebuild it from scratch. So this new version that you're seeing, lots of improvements. Instead of using DC motors with external absolute encoder gears, we switched to servo motors. That was kind of the obvious thing to do. The top plates hinge. So now if I'm working on it, I just open this up, voila. And I can swap out the battery and whatnot very quickly. It's a lot cheaper. So we shaved off $1,000. And I know $1,500 still sounds like a lot, but this is not just your cheap plastic rover. This thing can take a beating. This thing can go outside. This thing is made to last. You know, the mounting pattern, so the mechanical parts are made by a company called GoBuilda. We made that choice because we believe that they are going to stay in business for a long time, or we hope so at least, and it makes it very easy to build on top of it. So you can screw parts to the structure that they have there anywhere, which means that you can very quickly prototype stuff, you know, in CAD, and then buy it, try it out, and build your additions. Runs ROS 2 on the software side, and you know, this is not just like an embedded toy. It's like fully hackable, changeable, and people can modify the code and software at any level that they like. That took a lot of iterations to get there. On the mechanical side, trying to use only off-the-shelf parts to build something compact, strong, wasn't easy. And so we're lucky to have a bunch of people who are working on this, meeting on this every other week to make it happen. You know, we had to redesign the PCBs from scratch. So, you know, this was one of the first versions. There were several versions that went into this, and now we have this weird shape that allows it to fit inside of the body neatly. So it consists of two parts, the brain board and the motor board. And there were a lot of quality of life improvements, takeaways that we learned from building the first rover that made this one a lot easier. Being able to access the motor controllers through USB is a lot easier. We also added some new features. With the INA 260, allows us to monitor current, so now you can get a notification on your phone if your battery is about to die, which saves your battery. You know, being able to add LED lights to it, whatever you want to do. The last rover also had screw terminals on the side, so all the cables came in on the side of it, and so if you wanted to take your PCB out, you just actually couldn't. And so with this new version, you can plug out the cables from the middle and then unscrew the PCBs from the body, and you can take it out, make additions to it, fixes, whatever you would like. I don't even know what this was. It was a really cool YouTube video. There we go. Okay, well, it was a video of the rover driving around, but we'll do a little demo. I'll have people drive it around themselves. So how do you keep this change going? Like, how do you not just make something, keep it, and have it be stagnant, right? The lessons that we've learned over the years, over the last 5-6 years of doing this, is that you want to lower the resistance to change so much that it becomes easy for people who have never opened the pull request in their life, who've never contributed to an open source project. And there's a lot of people like that, right? Especially the young builders. We want to make it as easy as possible for them to make suggestions, make changes. And so what I see a lot of open source projects do is, like, you know, they're not very receptive to people's issues. You know, if you're not posting the issue in the right format, or your pull request doesn't look good, it's like, you know, ban him or close that stuff. So we really allow people to just say, you know, I can't figure it out on our Slack. I have a question. We have a long discussion about that where people try to figure out what's going on. And typically at the end of that conversation, there's some kind of improvement that comes out of it. And so it's really the simplest way, the lowest resistance way to create a fix. And typically what we see is that the person who suggested the issue, you know, who ran into something, will actually be so excited about the people helping them that they contribute it back, you know. And we help them through that process, because once someone creates a pull request once, they can do it 10 more times. We love that. And then sometimes you just got to show doing it yourself, right? Like, I've had people who, you know, had an issue but weren't quite sure how to fix it. And then you just show them, and, you know, after a couple of times, they figure out how to do it themselves. So it requires effort from maintainer side. And, you know, of course, we're incredibly grateful for people, volunteers, putting their time in to do something like that. So people who've made several contributions, we offer them to join the maintainer team. That happens a couple of times a year, that we have new people coming in. And that's amazing, because, you know, they become long-term members, and they help move things forward. What I've seen with larger pull requests, so if someone, everyone here is familiar with pull requests, right? yeah, if you're making a bigger change, it's often a balance of how do we get that awesome improvement in while also making sure that it's good quality. And that's kind of a balance that is tricky to strike, because we want to make sure that people, you're not keeping a pull request in limbo because it's not meeting your super high code standards. But you also don't want to just like merge it in and make it break or not have documentation. So trying to find that balance is typically tough. The way that we've kind of gotten around that is to ask the person submitting the pull request to make tickets for the future work, and that, I know that sounds like just putting it down the road, but that actually works really well. And also asking people, is this something that you're going to be able to update in the next 2 weeks, or is it going to take you like 6 weeks or more to fix this? And if the answer is it's going to take me a long time to make this change, we're just not going to do it. We're going to merge it in right now in favor of favoring speed instead of quality. And then maintainer meetings, to me, is absolutely essential. We get people together every other week on average. And it means that a lot of times the maintainers will get stuff done, because you know that the maintainer meeting is coming up, and so there's a little bit of pressure to get your stuff in order, get your pull requests merged in and whatnot. Also, we're always talking about updates and newer versions of the rover. So those meetings you have to make light and fun. Like if people dread showing up to this meeting, people are just not going to show up. And then I consider myself the cheerleader to this project. So I was kind of making people excited about submitting PRs. So hopefully I can convince a lot of you guys to join too. And then just recognizing that everyone is a volunteer. So, it's tough, but you can never demand people to get stuff done on time. Like sometimes it's just going to take a year. And if that's what it takes, that's how it's going to be. And yeah. So is this the last ingredient? I'm not sure. Kind of want to spice it up a little bit, but it's kind of a boring one. Documentation. But we really do pride ourselves on having some of the best documentation out there, and it's kind of the competition is kind of terrible. So you try to build an open source hardware project out there, a lot of times it's like, here's the files, go look at it. And what we've done is really try to make it as easy as possible for someone who doesn't have soldering experience to do their first soldering, for someone who doesn't have mechanical engineering experience to put this thing together. And so I just wanted to share some fragments of some screenshots of what that looks like. With pictures of, now that you've inserted these components, plug in the battery, put your test leads here of your multimeter, and it's got to look exactly like that, plus or minus a couple of volts, right, or millivolts or whatever. And this is how you assemble the mechanical parts. We have lists of like every screw that goes into every place so that people can make sure that they have everything set up correctly. And we found that helps people build this thing 10x faster than what we had before. This is really hard, right? Like if you're continuously making changes to this, but you also want to have detailed documentation, you're going to spend a lot of time having to redo the documentation. That's not a problem that I'm going to claim that we've solved. In fact, we just haven't. But there are some tools that have really sped this up, made this easy. I'm pretty excited about using Onshape. Before we were using SolidWorks, and I'm sure they've changed over the years. But this is really something that allows us to write less documentation. We put the model in there. For those who don't know, Onshape is basically 3D CAD for your browser. You don't need to download any software. You just open it up. People can look at it, zoom in, make cuts of the thing that they're looking at. And so we have to do fewer screenshots that we then don't have to update anymore. Fewer instructions. People can just look at this and build it. So we also like pointing to external instructions for installing like Ubuntu or Raspberry Pi OS on the Raspberry Pi. We used to like do that in detail, but now those instructions have gotten good enough that we just point to the relevant instructions so that every year when a new version gets released and the support for Raspberry Pi or whatever embedded board you're using changes, so people can, we don't have to keep redoing that. So let me talk about what it looks like to build one, just to show how easy it is, and hopefully a lot of you guys do it. So you're going to start by ordering parts from the various vendors, which means like there's a CSV file or Excel file or whatever that you literally drag and drop into DigiKey, and you hit add to cart, and then you add it in and buy it. You order parts from GoBuilda. If you're an educational builder, you get a discount from them. I think it's 15%. And those, we're working on them to make a build kit, but for now you have to click the links and add in the totals yourself. That shouldn't take too long. And then the PCBs we order from any online service that makes these for you, and they typically send them in like packs of 10. So you're going to have way too many PCBs, which means it's a good thing. You can mess up, you can make mistakes. You don't have to worry about it. It also means that you can just share with other people and cut costs even more. You're going to order the laser cut parts for the body, and then order whatever parts that you don't have that you want to use. Like if you want to use some kind of fancy RC receiver, that's the same thing twice. If you want to use a different gamepad, or you want to use a NVIDIA Jetson instead of Raspberry Pi, those parts you have to order. And then whatever tools you need. So there's no machining tools that you need anymore. There's no drilling required, no crazy stuff that you need to do yourself, other than soldering, being able to screw in screws and using a multimeter. So once you have all your parts arrive, the first thing you're going to do is kind of the most tedious thing, which is wiring. So there's a lot of motors in this thing. There's 10 motors, 4 servo motors, 6 drive motors. Right? This whole thing is independently actuated. I'm going to drive it off the table if I do this. Anyways, yeah, I'm not going to do that. So it doesn't fly yet. The helicopter is not working yet. So, we have like very detailed instructions. You've already ordered all the parts. They're there, and we have pictures of like this is the 5-volt cable, where the 5-volt cable comes in, along with diagrams that show it in detail. And then once you have all those cables, it makes it much easier later on when you're assembling the mechanical parts to route those through. I don't know if you're going to be able to see that from here, but these channels, these extruded parts have kind of channels in them that allow you to route the wiring in. And so you want to make sure that you've made the wiring before you assemble the mechanical parts. PCB assembly is kind of like the most daunting if you've never soldered a board before, and remember we have kids doing this. So lots of pictures again, and like grab this resistor and put it in this hole. And then that entire model exists on Onshape as well, so you can go and look at it in 3D and see exactly where that capacitor or resistor needs to go, along with explanations of what each part is and what it does. And along the way we're testing as well, so you're just validating that you're not messing up and that everything is working well, so that you're not putting it together and then like turning it on, it's like, oh, it doesn't work. And then the second to last part, mechanical assembly. So this is actually fairly easy. It used to be really hard because you have to screw so many different parts together. So you insert your wiring, you follow these great instructions on how you put it together. There's a couple of major components. The rocker bogies, that's probably the most complicated assembly here with this joint. And then you have your corner assemblies, 4 of them, and your drive motors. So you're going to make all of those separately, your main body and your differential pivot. And then at the end, you basically just screw all of them together. And there's detailed instructions on how to do that again. On the software side, once you've loaded everything up and you've configured some of the motor controllers, Go ahead.
So you're saying not to use the Raspberry Pi OS, using Ubuntu instead?
We recently switched from Raspberry Pi OS to Ubuntu because ROS 2 has um, has not just documentation, but they have like preferred platforms where they have Debian packages. So you can use Raspberry Pi OS, but it might mean that you have to install ROS 2 from source. So, 4? Oh, no, this is running Ubuntu 22 server. You are welcome to use whatever you want. It's very hackable. It's Raspberry Pi. But the reason that we do that is, again, back to the documentation. While what we used to have is like, here's if you want to install Raspberry Pi OS, and here's if you want to do Ubuntu, and here's what if you want to do Raspberry Pi 3 and whatnot. And what it meant is that we had to like maintain a lot of things. Like 1 year later, suddenly those instructions didn't work anymore. People would complain. And also someone who's new to Ubuntu, who's never heard of the term before, again, because they're 12-year-old, they're like, okay, now I got to figure out if I need to do Raspberry Pi OS or Ubuntu. I don't know, right? So what we decided to do is stick with one thing that works, document it really well, and the hackers are going to hack, right? They're gonna tear it apart and do their own thing anyways. So. Yeah. What's your GitHub handle? I'll await your PR. You're right. Yeah. Make an issue. No, I think it's a great point. And honestly, like again, I'm a robotics engineer. I'm not a embedded guy. So I've heard of Ubuntu Core before, but couldn't tell you much about it. Right? I'm used to programming big robots, not embedded systems like this. So, yeah. Sure. Like when you're saying virtual environments, like Python virtual environments, Docker, Nix. VM. Yeah, I mean, so what we could do is teach people Docker along the way or Nix. There's pros and cons to doing that. I think, for example, if I were to just pick Docker, there's a learning curve associated with it, and I wouldn't say it's the easiest when it comes to working with real hardware. You have to do all your file forwarding so that mounting that people can access the serial ports and whatnot. Sure, and so we could do that, but then we're already teaching people who are new to robotics a lot. So if we also have to teach this additional tool, what I'd rather see is a builder coming in and saying, hey, I've done this entire thing in Docker and it's better for these reasons. And then someone could come in and say, I'm going to follow this guy's instructions. So that's kind of the approach we're taking. Yeah, yeah. Right. Yeah, I think if it gets to the point that it's just obviously better than the approach that we're taking, we will make it the default. So. Uh-oh. May or may not have system D on there. That's right. So you're gonna SSH into the Pi, and then install ROS2. So hopefully that is all very simple, and we literally just put the commands that you need to copy paste in your terminal there. Compile it, which is like the ROS2 command calcon build. Test your serial connections and I2C connections, and then there's some calibration steps involved for making sure that the corner motors are going straight, and your drive motors are getting the velocity that you want to go. And then you run it, and then don't mention the system these are. Question. Once. Yeah. That's one of the reasons that we went with this with these servos, because they remember the offset internally, absolute encoder. And that's it. And that's, for someone who's new to robotics, embedded software, all that kind of stuff, this is the gentle introduction to full stack robotics in just a few weeks. And that's awesome. That's actually the original mission that JPL set forth, is to, foster the next generation of roboticists that they can then hire, of course. So, and then last ingredient, passing it on, teaching others. And this is kind of that where it goes into, hey, like I built my Docker or Nix or whatever environment for this, or I've added this cool addition, sharing it back to the community. And that's really important, because it gets, again, people excited, which is the first ingredient. So let's take a look at an example. This map in the bottom left was I generated with the old rover a couple of years ago. Wrote a blog post about it. SLAM, for those not familiar with it, simultaneous localization and mapping, very commonly done in mobile robotics. You're going to build a map for your environment so we can navigate in it. And I wrote a blog post about it, again, to kind of share people how to get started, how to do this easily, and then teach people some like basic robotics concepts that hopefully they take away for life. So one of the issues with SLAM, or the thing that SLAM and sensor fusion do, is I have all these sensors that record where I am in the world. For example, when my wheels are spinning, I know that I've moved this amount, and I can make an estimate of where I am. And then if I mount a LiDAR or a camera on top, I can also record how much I've moved. So fusing those two things together, building a map, and knowing at the same time where you are in that map.
How would something like this work in an outdoor environment where you might have rises and falls and then
Yeah.
plants in the way and stuff?
Totally, and it's kind of funny because I've been touting this thing as an outdoor rover, and now I'm doing like indoor robotics. Yes, absolutely. This is why we don't include a sensor stack. We don't put a camera on there or a LiDAR on there for people to do. We just create the basic concept, and if people want to do an outdoor robot, they're probably going to pick a 3D LiDAR or a monocular camera or RGBD camera that they can put on there. And we have thought about that, and the PCB has outputs so that you can power those electronics, whether it's 5 volt, 12 volts.
You have like, USB take that connector to
Yep.
plug all this.
Yeah, Raspberry Pi has that, yeah. Does it have an IMU? No, it doesn't have an IMU. You can put an IMU in it. Yeah, but if I'm building this rover and all I'm going to do is drive it around using my gamepad, I don't care that there's an IMU in it. Plus, it adds to the cost. I want to have as many people build this as possible. Okay, so one of the things that people get wrong all the time is when they're doing this sensor fusion, is to get into the fancy, cool algorithm stuff immediately, right? You have like this LiDAR information, and I have my monocular camera, and I got my wheel odometry, and I'm going to fuse them. And it doesn't work as well as I do, so I like go and find the fancier algorithm, and I add a cooler sensor stack on it. But a lot of times the reason that it's not working that well is people skip their basic steps. They're not doing their wheel odometry right. And so one thing that I wrote about is analyzing odometry, and it's actually a fairly complicated subject to get it right. But something as simple as when I'm telling my wheels to move this fast, is it actually going at that speed? And that's not always obvious. You know, how do you go and measure the velocity? And again, my video is not loading, which is a bummer. I guess connecting the Wi-Fi would have been a good idea. So the thing that the video would show here is a way to measure velocity, right? How do you go and look at, I'm setting this wheel to go at 1 radian per second, you know, some degrees per second. How do I actually see how fast my wheel is going? Well, you can read the encoders and see how fast it's going, but you might make mistakes there. And if you're using a quadrature encoder, it's not telling you radians per second. It's giving you some kind of pulse per second idea, and then you have to see where it's mounted on your gearbox and make sure that you're doing that conversion right. So anyone, any ideas? If I'm spinning this wheel pretty fast, how do you measure it? How do you actually physically see how fast it's going? Yeah, this was a video of a tachometer. You stick a little thing on it, and then you can measure how fast it's actually spinning. So that's super useful. Say again?
You have servo loops, I assume, in this thing that rely on the encoders?
The servos actually have a chip in them that does the velocity control themselves. For the drive motors, the control happens on a separate microcontroller. Yeah, we tune those loops too. But again, you want to actually measure how fast is my wheel going, so you know you're right, because there's also going to be issues with that being offset. So the other one that I wanted to show, and it's also not going to work, is using a strobe app on your phone. So this is kind of a cool one where you actually put like a little reflective tape on your wheel. You spin your wheels and you can adjust the frequency of the light on your phone to go a certain rate. And what you get is that kind of effect where if you're matching the frequency of your strobe light, you will see the tape that you've put on there light up at the same rate, and it'll start forming a line. The same way that when you're driving on the highway and you kind of see a car wheel suddenly stop even though they're really fast, right? It's the same concept with the strobe light, and it's kind of a low-cost, sciencey, cool way to measure if your wheels are going that speed.